So today we will study about the failure, and we will study how it occurs, right? Why the things fail. If we have some system, we have some structure, why it fracture, and the way the mechanics of fracture, right? Fracture mechanics we will study. What is the reason, and what types of fracture, what types of failure we have in different material, right? So these things we will study today. Here you see you have different photos, some plastic packages. You see here, this one, here and here. Now you might have experience to cut or to open this plastic package, right? Which contains anything. You might have like sugar, some this tank pack and shampoo or something. So have you experienced to cut it, right? I hope every one of you might have. So what happens? Sometimes these packages you can open it very easily, but sometimes it becomes very hard, right? And when it becomes easy, when you see the small incision or small cuts, you see here, and if you try to cut from this section, this part, you can easily cut the package. And if you try to cut from here, it is very difficult, right, to cut it. So you probably have noticed when a small incision or cut has been made into an edge, as appear in the photograph. You see here. So then we need minimal force to tear the package or to open the package. Otherwise, we need more force to open the package. So this phenomena, when we have a small incision and then to open the package, it requires less force or minimal force. This is one of the you can say the criteria or one of the tenets of the fracture mechanics. So the applied tensile stresses is amplified at the tip of the incision. Now here we have this incision, so this is the tip. You see one side, if this is the incision, so this is the tip and this is the tip. Once we apply the stresses, these stresses are gets amplified at the tip of the notch or incision or cut. So that's why due to the amplified stresses, the package opens easily. And this here, if you look at, we are opening, but this is failure, like somehow we are failing the package opening, right? Now the same thing. It means whenever there is a crack, there is a small incision, it can lead to a failure. Now here you see the oil tanker, and it has been fractured like in a brittle way. As a result of propagation of cracks, right? So there was a cracks here, and that cracks propagates, and then the oil tanker break into two parts. This crack started as some type of small incision, a small flaw or sharp flaw. So there was a small incision, a small cut, you can say, a small crack was there, and that crack propagates. So when they, like there was the oil tanker, when they bobbed it about to the sea, the stresses becomes amplified. We are at the tip of the notch, right? And that makes the thing fail. And the whole tanker was separated into two pieces. And it was brittle. We will study today what is brittle fracture and what is ductile fracture. So brittle fracture, usually it does not give you alarm. It does not give you any clue that the system, the structure is going to fail. You will not see the necking. Suddenly it failed. So here was the thing, there was a cracks, and the cracks gets propagated. Now keep it in mind, all material, whatever material we have, they have microscopic cracks within the material. It is not a flaw, but within the material, microscopic cracks are always available. And that cracks can be propagated anytime due to stress. So while designing the system, we have to take care, we have to bring in our notice that there are microscopic cracks. Here is another example. You see the photograph of Boeing. So this was a commercial aircraft that experienced an explosive decomposition of structure failure on April 28, 1988. And you can see the image here. So an investigation of the accident conducted caused that the failure was metal fatigue. That was intensified by crevice corrosion and as much as the plane operated in the coastal humid environment. Now metal fatigue, we will also study the fatigue here in this lecture. In this part, not today maybe, but in the next week, but in this part of the course we will study fatigue also. Now fatigue is the cyclic load when we apply to a material. So that cyclic load fails the material. Now we know that the material will fail when the stress level reach the ultimate tensile stress. We have studied this, right? And then there will be necking, and after that, at some point the fracture can occur. But in some scenario, like there is a fatigue, there is a cyclic load. If you just bend it, the material in this way and then bend it again. If you do it, so the stress level can be very low as compared to the ultimate tensile stress, but the material can fail because of the fatigue. So we will also study this, right? So stress cycling of the fuselage resulted from the compression and decompression of the cable during the short half-flight. So during the flight, there was a compression and decompression. One cycle means one compression and then decompression. So the stress level was very much low as compared to R from the ultimate tensile stress, but the material failed. So we have to take into consideration the fatigue also. So a properly executed maintenance program by the airline would have detected the fatigue damage and prevented this accident. Now in all the structure, if it is aeroplane, if it is a bridge, if it is anything, we need a proper monitoring system. We need a proper maintenance system. So if there is a maintenance system, we would have known that the material is about to fail. Right? If there is compression and decompression continuously, so we should know that this fatigue and this fatigue can lead to a failure. So in all the things, first what we have to do, we have to keep these things like fatigue, if there are cracks, whatever thing, we have to include all these information in our design while we are designing the system. But apart from all these, we must have our proper maintenance system, proper monitoring system to avoid these types of failure. Here is another example, this Silver Bridge in 1967. You see here the bridge, and then after some time the bridge collapsed. If you open the PowerPoint slide, this is in PDF, here in the notes, I have put the complete story, and this bridge collapsed because of the crack propagation. There was a cracks and propagation. So you can read the story there in the notes. Now the question is, why we study failure? Here we are starting the failure, these were some case studies, but why we study? So we study it once we are designing the component, or we are designing any structure, or an engineer has to design any structure, any system. So we want to minimize the possibility of failure. So if you want to minimize the possibility of failure, for that we need to study the failure. First we have to study, we have to understand, then we will be able to minimize the possibility. So that's why it is important to understand the mechanics of various failure. We have to understand the ways, why the material failed, the mechanics, how it failed, different types of modes. Like it failed because of fracture, because of fatigue, because of creep. We have to understand this mechanics. Then we will be able to minimize the failure. Otherwise, if we don't understand why it failed, then we cannot minimize. And in addition, we must be familiar with the appropriate design principle that may be employed to prevent this in-service failure. So that's why it is important. We have to study the failure to minimize the possibility of failure in any structure, in any system, in any component. Right? That's why we study it. Now here, we will start proper introduction to the topic. Now, the failure of engineering material, usually what fail? The material fail, right? So from the material, we make any component, we make any structure or any system, we make it from the material. So whenever a material fails, it has a lot of effects. And if you are working in any industry and let's say some material failed there, some system, some structure failed, it will have effect on the human life, right? It can put the human life at risk. There will be losses, financial losses will be there, right? And there will be interference with the availability of products and services. If you are working in an industry and there some failure occur, there will be problems in the availability of, if the industry is providing services or products, of course there will be problem and it will affect. So that's why we have to understand how to avoid failure. And if the failure occurs, then there will be shutdown of the system and you have to do the maintenance and all these things, which takes a lot of time. So we don't want these things. That's why we are studying the failure to minimize the system, any failure in the system. So sometimes we know the causes of the and the behavior of the material in which it can fail. And those behavior, those causes of failure, sometimes they will not guarantee that the material will not fail. And apart from all those things, the material still fail. Why? The usual causes are improper material selection. Now, if you are using, let's say, some type of some grade of steel, now you know that this steel can break it. Let's say the ultimate tensile stress is this much, and the fatigue life is this much. But if you have chosen the steel for wrong material, wrong system, like the system has to be made from some other grade of steel, and you have used some other grade of steel. So the improper material selection, and improper material selection can lead to failure, can lead to the economic losses, can lead to the can put the human life at risk. Now the damage can occur to the structural parts during the services, and we need regular inspection, we need to repair, we need to the replacement of critical component. So the important thing, what we will study in this part, we will study starting from the simple fracture. What is simple fracture? Right? From the very basic, and we will study then the ductile, the brittle fracture. We will study the fundamentals of fracture mechanics, fracture toughness, and its testing. We will study how the ductile to brittle transition happen. Usually the fracture occur from the ductile to brittle transition. So sometimes the material will behave as a ductile, but at some temperature it can be brittle, like what happened to the Titanic ship. We will study the fatigue, the creep we have already studied, so we will not study it here. So all these topics we will study in this part, right? Now starting from the first thing, the fundamental of fracture, the simple fracture, right? What is simple fracture? Now, And why we say that there is a failure? What happens actually? Now, simple fracture is the separation of body of any system, of any matter, you can say, into two or more than two pieces. If you have this shaft, right, and let's say it breaks into two pieces, it means that there is a fracture. So now, why it will separate into two pieces? When it is exposed to some stresses, right? When it is exposed to stresses, it can fracture into two pieces. So simple fracture is the separation of body into two or more pieces in response to an imposed stress. Sometimes when the material is exposed to temperature. Now all these, when it is exposed to stress, when it is exposed to temperature, we use one word. We say that when the material is loaded. Now loaded can be when it is exposed to temperature, when it is exposed to any physical phenomenon. So when you load a material, the simple fracture can occur and the material can break into two or more than two pieces. Now fracture can also occur from the fatigue. You might have experienced if you have, let's say, any metal wire or any paper clip you have, and if you bend it in this way and then again, if you bend 2-3 times, you can easily break it. And usually when we are breaking something, we do this process, right? We bend in this way. And it breaks easily. Why? Because there is a cyclic stresses, which is known as fatigue. We will study the fatigue in detail. And the fracture can also occur from creep, like time-dependent deformation, which we have studied. We put a load on the material and we leave it for some time. So this is time-dependent deformation. Due to time-dependent deformation, the material can fail. And this normally occurs at high temperature, right? Now, when I say that the material is loaded, means we applied some stresses. The stresses can be tensile stresses, can be compressive, can be shear, can be torsion, or combination of these. So these types of stresses we can apply to a material, and then the material can fail under these types of stresses, or combination of these types of stresses. So this is simple fracture, right? Now this simple fracture, when we are studying from the material perspective, we have ductile and brittle fracture. Now what is ductile and brittle fracture? You know which material is ductile and which material is brittle. We have already discussed it. Now for metals, we will be discussing most of the things for metals here. So for metals, two fracture modes are possible. One is ductile and the other one is brittle. Now why there is this classification? So this classification is based on the ability of a material to experience plastic deformation. When a material fails, let's say I have this pin, I applied tensile load from here and from here. If this material is ductile, so what will happen? First, you will see that the length of the material will elongate. And then at some point, you will see the nicking, which is permanent deformation, the plastic deformation. So you will see the nicking. If this is the specimen, if this is the specimen and you applied the force from here and here, so you can see this nicking, which you already experienced in the tensile testing. So this plastic deformation is there. So based on it, whether the material is experiencing plastic deformation or not, we have divided the fracture into two modes, ductile and brittle. Now ductile metals, typically they exhibit substantial plastic deformation with high energy absorption before fracture. Now what happened? When we see the plastic deformation, the material absorbs energy before it fracture. And such cracks, when the material, if we have a cracks, right, and the material fracture is ductile fracture, or we have see that the material is ductile, so that crack is often said to be stable. Why it is stable, that crack? Because that material, when it fails, it will give you some alarm. Alarm means you can see it that the material is going to fail. After 1 minute, 2 minutes, or after 1 day, 2 days, the material can fail. You see this plastic deformation, the necking and all these things, right? While on the other side, when there is no plastic deformation, you just apply the force to the material and suddenly it breaks. Means low energy absorption. So the material will not absorb much energy. So that types of cracks is said to be unstable cracks. The unstable cracks mean that cracks can propagate at any instant of time. Without giving warning, without alarming, it can break. That's why it is known as unstable. Now the ductile fracture is almost like always preferred to the brittle for two reasons. We want the fracture to be ductile so that it should absorb much energy in the plastic deformation. Right? For two reasons it is preferred. The first one is the brittle fracture occurs suddenly and catastrophically without any warning. As I told you, the brittle fracture, it will not warn you. It can fail the material at any time, right? While on the other side, the ductile fracture, it gives you warning. It alarms you, right? That the failure is coming. So if it alarms you, if it gives warning to you, what you do? You can do the preventive measure. and then you can either avoid, or if you cannot avoid, you replace the component and you save either the economic losses, you save the human life, or you save any other types of losses which can happen due to the accident. And the second thing is that more strain energy is required into ductile fracture, and as much as these materials are generally tougher. Ductile materials are generally tougher, right? Why? If you see the curve, what we do for the ductile material? We have this type of curve. So if you see, you find all this area, this is like the material toughness. While for the brittle material, we see this type of curve, only up till here and then it breaks. And if you find this, this is the toughness. So here we have much toughness, more energy is absorbed by the material. While here we see very less energy absorbed by the material. So these are the two types of ductile and brittle fracture. Clear? Okay. Any confusion to anyone? Are you all with me? Okay, look here. The brittle versus ductile failure, the classification here, we have some images, like we have very ductile, moderately ductile, and brittle fracture. Now in the very ductile fracture, what happens actually? If you have the material, you apply the stress, the load from here and here. So you will see the necking. This is the necking, right? And then the material is going to fail. So theoretically, there is 100% area reduction. The area reduction or percent elongation, it is 100%. If this is the area, initial area, if you look into the area at the fracture, so the area is reduced 100% theoretically. Right? So this means this is very ductile material. And the behavior of the fracture is very ductile. You can say that the fracture is very ductile. Because you see the more area reduction, the more percent elongation is there. Right? The necking process is very much clear to you. You see the plastic deformation there. And this type of fracture, we prefer this type of fracture. Because it warned us, it gave us warning that the material is going to fail, so do some preventive measure. Then we have the moderately ductile. In the moderately ductile, the area reduction and the percent elongation is moderate. Not like 100%, a little bit less, but still you can see the necking, right? And then it fracture. There is a little bit permanent deformation and then it fracture. The next slide, we will study how it happens. And the last one, we see the brittle fracture. Brittle fracture, you see theoretically 0% elongation. The area reduction or 0% elongation. Once you apply the load to the material, it fractures suddenly. And you don't see any alarm, any warning, right? So that is known as brittle fracture. You see here, we don't have any types of warning. Here, warning occurs before fracture. And this warning is very important. If you know that after some time the material is going to fail, so you will do the preventive measure and you will save a lot of things. Once you don't have any alarm, once you don't have any warning, you cannot save anything. Right? Now, the highly ductile fracture, you see here, as we discussed in the previous image, we have the highly ductile fracture. In this type of fracture, the material nicks down to a point fracture, showing virtually 100% area reduction. This I already explained. You see, at this point, the area reduction is 100%. If this is the total area, here the area is reduced 100%. Theoretically, it is not 100%, but we can say that too much area reduction is there. And these types of fractures occur in extremely soft material, soft metal. As I told you, we will be discussing most of the things for the metal, such as gold, lead. So these two materials can have the highly ductile fracture at room temperature. And other materials like polymers, inorganic glasses, they can have the highly ductile fracture at elevated temperature, at high temperature. Right? So this is highly ductile fracture. Now the moderately ductile fracture. Look here how it happened. Why we see this type of shapes here. Now the moderately ductile fracture, it occurs because first the cracks form and then the cracks propagate properly. So initially what happened? Once we have the specimen, we apply the force. You see here, we are applying the force. So we see the necking phenomenon. So this is the initial necking. You see here. So there is initial necking. After the necking, what happens? How it failed? So look here, we have the small cavities. After necking, small cavities are formed. We also call it microvoid. So these microvoids are small cavities. So we have one cavity here, a lot of cavities are here. But still we are applying the force. The force is the stress or the force, you can say, continuously we are applying. So once these cavities are formed, and then if you continue to stress to increase the stress, what will happen? These cavities, they will come close to each other. They will combine, right? And these cavities, once they combine, they form cracks. So then we have cracks here. You see, this is crack. So initially we see the necking, then we see the small cavities, and then those cavities combine to form a cracks. And if you still continue, the stress still continues. So what we see the crack propagation. Then this crack propagate in this direction. You see here, the crack propagates. And once the crack propagates, and still if you continue the stress, so at some point, the fracture will occur and the material will fracture. Here we see the fracture. Now, in the moderate ductile fracture, the final fractures occur at 45 degrees. You see, here we see the shear. So the force we are applying in this direction, the fracture occurs here. So it occurs at 45 degrees relative to the tensile direction. This is the tensile direction. Now, one important thing, if you look into this fracture, what is happening? You see this curve? This is like a cone, you know, and the other type seems to be a cup. You see, so this material fracture in this form, it forms cone and a cup. You look here, we have an aluminum material and how it fractured. This is the moderately ductile fracture. This side is known as cone and this is cup. So cup and cone fracture is also known to the moderately ductile fracture. This is the mechanism how this fracture occur, right? Or you can say that this is the fracture mechanics of moderately ductile fracture. Any confusion to anyone? You understand, right? If I ask question, then you will not say that the questions are not clear. You have to understand these steps. First, the necking occur, then we see the small cavities, then the cavities come close to each other to make a cracks, then the crack propagates, and then the fracture occurs. But in all these processes, what will happen? The only thing, the stress is continuous, right? We are still applying the stress. If you leave the stress here, if you remove the stress at this point, then the crack will not form. The cavity will not come close to each other, right? And then it will be as it is, like the cavity, if you don't apply the stress. So in all this process, the stresses we are applying continuously. Clear? This is how we study the fracture mechanics of the moderately ductile fracture. Now one more thing. We have the fractographic studies of ductile fracture. Fractographic studies of ductile fracture means once the material fracture, once it breaks into two pieces, then the fracture surface we see under the microscope. And that microscopic studies give us some important information. Right? So the studies of the fracture are the fracture surface under microscope is known as fractographic study. Now here you see we have the two images, this one and this one. These two images are taken using the scanning electron microscope. And the figure A, this one, it shows the characteristic of ductile fracture resulting from uniaxial tensile load. So due to ductile fracture, and what happens, you see this is the 3300 times resolution. So using scanning electron microscope, when we see the image of the ductile fracture, we will see this type of structure. Now this type of structure, what is here? We see dimples, right? Look here. So when the fibrous centrous region of cup and cone's fracture surface is examined with the electron microscope at high magnification, it will found to consist of numerous spherical dimples. You see, we have different types of dimple. If you study the cup and cone, this surface, right, under microscope, so it will give you a lot of dimples, and you will see with your eyes, right, under the microscope, that the dimples are formed. Now those dimples, what are these dimples, right? Actually, these dimples are the microvates, are the small cavities. You see here, look here, we have the cavities. So if let's say the fracture occur here, and then you are looking to one side of this under microscope, so you will see that the cavity is formed here, 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 and here, and you will see the small dimples under microscope. These cavities are microscopic cavities, right? We are talking about microscopic cavities, and once it forms, right, and make a crack, and then the crack propagates, it will be macroscopic. Then we can see with naked eye. But initially it is microscopic, right? So you will see in the fractographic study, you will see this types of image. There will be a lot of dimples. Now the dimples also form the 45-degree shear lip of the cup and cone fracture. As I told you that the cup and cone fracture, what happened there is at the final stage, it shear at 45 degrees to the tensile load. However, these will be elongated or C-shaped as shown in the figure B. The parabolic shape may be indicative to the shear stress. So when it gets elongated, we can also see the parabolic shape. You see different types of parabolas. So this is also for the cup and cone structure. Right? So the fractographic studies, we do it, right, to verify, to see some more information. You see the figure B, the scanning electron microscope showing parabolic shape dimples characteristic of ductile fracture resulting from the shear load. So why we do it? Now, this is very important, right? Why we do the fractographic study? Sometime you are working in an industry, and in industry, let's say some shaft failed, it fractured. But you are not sitting there and looking into the shaft that how it failed. Is it ductile or brittle? Is it cup and cone? What types of fracture is it, right? You don't know. But suddenly something happens and there was a fracture of the shaft, and you came to know that here the shaft is fractured and the industry, the plant is stopped. Now what you will do? For the time you will replace the shaft, but the broken one you will bring it to the laboratory, and now you have to study why it failed. What types of fracture was it? So in that scenario, this fractographic study is very, very important. It tells you more information, how the material failed. And then you, in the future shafts or in the future material you are using, you take these information into consideration and you try to minimize the chances of failure for the future material. Clear? Any confusion, guys? Okay. I hope everyone is with me, right? Not sleeping, enjoying Ramadan. Then we have the brittle fracture. Now, in the brittle fracture, what happens? As I told you before, in the brittle fracture, we will not see any type of necking, any type of plastic deformation. At fracture, suddenly, you see here, this is the mild steel fracture. These are the two pieces, and the shaft break into two pieces, right? So look into this surface and this surface. It is flat. It means if it is flat, it means suddenly it breaks. There was no warning, there is no alarming, and the material failed. So brittle fracture takes place without any applicable deformation and any crack propagation, right? So the crack propagation here, once it is, let's say the crack generated here, it propagates very rapidly. You will not see like the crack is propagating and you will see it. No, it rapidly propagates and suddenly fractures occur. Now the direction of crack's motion is very nearly perpendicular to the direction of the applied stresses. This point is very important, right? Now if I have the material, look here, this is the material, right? I will draw it here, look. This is, let's say, the specimen, right? And you are applying the stresses in this direction and in this direction. So if we see the crack, let's say the crack generates here, this thing occurs instantly, like very rapidly. But if the crack is here, so usually this crack propagates perpendicular to the applied stresses. Now the applied stress is in this direction. So perpendicular to this is this direction, right? That's why we see flat surfaces. We don't see the cup and cone. It is not at 45 degrees. It is perpendicular, like at 90 degrees to the applied stresses. So the crack propagates perpendicular to the applied stresses when there is a brittle fracture. So the fracture surface of material that fails in a brittle manner will have their own distinctive pattern. Any sign or gross plastic deformation will be absent. So it has its own pattern. We don't see the plastic deformation. And the own pattern is what? You see here, this is the points where the fracture gets initiated. And then suddenly it propagates in circular part. Like you see making a star. If it is here, let's say this is the point where the crack initiates, it propagates in this way. It makes like a star type structure. You see here, you will see some line, right? This is where the cracks initiate this point and then it propagates suddenly. And sometimes we see a series of V-shaped chevron marking from near the center of the fracture across, like the cross section. You see this, and this shape is known as like the chevron shape. So this point, you see where we have the arrow, this point, and this point. These are the points where it gets started. And then it propagates and the material fails. So this is all these information are brittle fracture. Now these photos, they are not like the fractographic study. They are the real-time images, right? They are the real-time images, not zoomed one. One more thing, the very important thing. We have two other types of fracture, which occur mainly in the crystalline material, right? One is transgranular and one is intragranular. The transgranular fracture means if you see the metal, we discussed in the structure, the crystalline structure, that if you look into the microscopic structure, you will see different types of grains under microscope. So these are the grain, like this is one grain, you see, this is another grain, right? So these are the grain. Now in the transgranular fracture or transcrystalline fracture, what happens? The crack propagates in this direction, that it is not propagating along the boundaries of the grain. Randomly it passes the grain, right? You see here, the schematic of cross-section profile showing the crack propagation through the interior of the grain for transgranular fracture. So it is passing from the interior of the grain, like the grain is breaking into two pieces, right? It is not following the boundaries. You see here, the crack is not propagating in this way. It propagates in any direction, right? Or here. So the grain is breaking into pieces. That's why you look here, the microscopic image, you don't see clearly the grains. Why? Because the fracture was transgranular and it occurs like the crack propagates in between the grains. While on the other side, we have another one, the intergranular. The intergranular fracture, what happens? The crack propagates along the boundaries of the grain. You see, if there is the fracture, so this will propagate along the boundaries of the grain. And when it propagates along the boundaries of the grain, and then if you do the fractographic study, you will see clearly the grain. You see here in this image, you can clearly see that this is crystalline structure, and you see the grains very clearly. Why? Because the material fracture or the crack propagates along the boundaries of the grain, along the grain boundaries. So this is intergranular, right? So these two types also it is important. Maybe I will give you in the exam or somewhere tomorrow you will see the microscopic image, right? And you have to understand whether it is intergranular or it is transgranular. Clear? Okay, good. Now tell me, all of you are with me or only these few guys? Guys? Okay, good. So now we will continue the principle of fracture mechanics, right? We have to study here the mechanics, how the fractures occur, what actually happens that the material fails, right? So the brittle fracture of normally ductile material, this is the important thing. Usually the ductile material, if the fracture is ductile, so it is okay. We will have a warning. We know that the material is going to fail, so we can do the preventive measure and we can avoid the accidents. But sometimes the brittle fracture occurs for the ductile material, right? And why it occurs, that thing we have to understand. That is very important. So the most important thing that which I want to tell you, the fracture will always occur as a result of crack propagation. Now cracks come from where? All the materials, whatever material you have. So microscopic cracks are always present in the material, right? Microscopic cracks are always present in the material. And when the cracks propagate, the material fracture, the fractures occur. Now these cracks, when it will propagate? When we expose the material to the tensile stress, right? And the magnitude of the applied tensile stress amplified at the tips of these cracks. So as I told you before that if let's say we have, this is the crack, so this is one tip and this is another tip. So if you apply the stress, so the stresses will get amplified at those, the tip of the cracks. As I showed you the small packs of the sugar pack which you put it in your coffee, if there is a small incision, that small incision is not what we consider it as a crack, right? But macro crack, not micro crack. So that macro crack, if you apply a force, so the package you tear at that point. Why? Because the stresses gets amplified at the tip of the crack, at that particular point. So people, the material scientists, they have done complete research, and they came up with a new field which is known as fracture mechanics. Here we are just having an introduction to the fracture mechanics, but at higher level, you will study like the complete book, the complete course of fracture mechanics, right? And this fracture mechanics tell us how the fractures occur in the material, how we can avoid the accidents, right? How we can prevent the cracks from the propagation. So all these things we study where? We study it in the fracture mechanics. Now look here. Here is the important thing. Now the fracture mechanics, we say that the cracks act as a stress concentrator. This is the same word which I told you before, that the stresses gets amplified at the tip of the crack. So in other words, we can say that the cracks act as a stress concentrator. All the stresses, they concentrate at the crack. We are at the crack, at the tip of the crack. Now the maximum stress at the tip of the crack, we can calculate using this formula. This is sigma m. It is the maximum stress at the tip of the crack. Now you see here we have this material. This white is the crack. So the tip of the crack is where? You see this one, x and x dash. These are the two tips of the crack, right? And here you see the rho t is the radius of curvature of the crack. Like this is the radius of the curvature. If you see this is the crack, so this here we have the radius of curvature of the cracks. And we have the applied stresses. Whatever stress we are applying to the material from here, you see, and from here. These are the applied stresses. Now what is the length of the crack? You see here the length of the crack is 2a. From x to x dash, this length is 2a. So the maximum stresses are equal to 2 sigma naught a divided by rho t. Whole under the root r whole power raised to the power 1 over 2. So this formula we will use to find the maximum stresses. Why we find this maximum stresses? The stresses at the tip of the crack. For every material, there is one value known as critical stress, which we will study in the coming slide. So the maximum stresses, while we are designing anything, the maximum stresses should not be more than the critical stress. By maximum stress, what do I mean? The stress at the tip of the crack. The stress at the tip of the crack. This stress should not be more than the critical stress. If it is more than the critical stress, what will happen? Can you tell me what will happen? Fracture. But before fracture, the crack will start propagating. right? Hussein, the crack will start propagating if the stresses at the tip of the crack is more than the critical stress, right? So the cracks will start propagating. Now, I told you before that when we have the applied stresses, this is the tensile stress we are applying. So at this point and this point, we will see maximum stresses. How it happened? Look here into this figure. In this figure, it is very much clear. So we have plotted the size of the specimen. This is the width, you can say x dash, the width of the specimen. And on the y-axis, we have the stress value. Now look here, we have, this is the crack. This is the crack within the material. So we want to know where we have the maximum stresses. Now the stress, if you look here into the y-axis, the stress starts at sigma naught. It will not start from 0. Why? Sigma naught is the stress value which I have applied to the material. If I have the specimen and I applied the stress like 2 megapascal, 3 megapascal, 100 megapascal, so my stress will start from where? From 100 megapascal, right? Not from 0. So it starts from this point. And it starts from this point and it goes in this way. Why it goes in this way? Look here. This is, if you look into the specimen, this point is what? Here, this point. Now, when we are approaching to the crack, like we are from here, we are moving toward x. This is x, right? So what happens? We are going toward the tip of the crack. And as we reach, once we reach the tip of the crack, so we see that the maximum stresses are at the tip of the crack. So from here, the stresses are getting going up, increasing. And when we reach the tip, we have the maximum stresses. Same from the other side, if we are coming from this side. So here we have only the applied stresses, and the stresses are getting going in the increasing direction, like getting increase. And when we reach the x dash, which is the other tip of the crack, at this point, we also have the maximum stress. So you see here, this is the specimen width, right? And this x and x dash is the tip of the stress. Once you plot the stress value, you will see that the stresses are maximum at the tip of the crack, right? So we have the maximum stresses and sigma naught is the applied stresses. Now sometimes we have a ratio of sigma m divided by sigma naught. Sigma m is the maximum, sigma naught is the applied. And is denoted by a stress concentration factor, right? Which is known as Kt. So this Kt is the stress concentration factor. Stress concentration factor you can find, how you can find? By, it is a ratio of sigma m divided by sigma naught. And now here we found sigma m. Sigma m is equal to this term. So you put sigma m in this formula, you will get this. Right? So this term is known as stress concentration factor, which is simply measure of the degree to which the external stress is amplified at the tip of the crack. So sometime in the design, we use the stress concentration factor. Is it clear? Any confusion? Okay, good. Now here is one more thing. All these things we studied, right? What we have to do to avoid the fracture. So when we are designing something, right? So from fracture point of view, what we can do? We can do the first thing which we will study here is avoid the sharp corner. Avoid the sharp corner. If this is the component you are designing, so here let's say you have the corner. So always try to keep the corner, let's say this is the corner, don't keep it the sharp corner, this is sharp corner. Use fillets. You see here? These types of fillets, right? You might have studied it in the solid ones. So always try, wherever possible, use this one. Why we use this one? I will explain. So look here, we have the stress concentration factor, Kt, and here we have the sharper fillet radius. So once you are decreasing the fillet radius, you see here, if you are going in this direction, so you are decreasing the fillet radius, means the corner is sharper. If you keep the corner as sharp as whatever you do, you will have the high stress concentration factor, which you don't want. So the ratio here is high, you see? And as we are decreasing the increasing the fillet radius, we are going in this direction, the stress concentration factor is getting reduced, right? In this way. So we don't want high stress concentration factor, we want low stress concentration factor. Now what is the mechanics here? Yes, here I will explain why we want the fillet, why we don't want the sharper edges. Now look here, if you have two material, one material is having the sharper edge and another material is having the blunt edge. Now what happens if you apply the stress in this direction, let's say you are applying the stresses and here also you are applying the stresses, right? Now which one will break faster? The sharp one. Why? What is the reason? Why this one will break faster and this one will not break? Stress edge. Yes, but the reason here, what is the reason? The reason is, if you look into this part, So how much material is exposed to the stress? Only this corner, you see, very less material, very less area is exposed to the deformation. So once you apply the stress, suddenly it will break, because the whole force, the total stress is concentrated here at this point. While if you see here the stress is not concentrated at this point. All in the whole region, you see here, are in this image. It is on the whole region. So we see the deformation, the too much deformation here. So this part also deformed, this part also deformed, this part also deformed, this part and this part. So that's why the stress is distributed over the area. Here, the stress is not distributed over area. The deformation only occurs at that particular point. So if you apply the same amount of stress to this material and this material, this one will break faster as compared to this. So that's why in the design, we are trying to avoid the sharper corner. We are trying to avoid the sharper corner. This is very important point. Whenever you are designing anything, right? So if it is possible, you have to avoid the sharp edges, the sharp corner, right? Is it clear? Okay, one more thing and then we will stop. Because the previous class I have explained up till here. Now we have the criteria for the crack propagation. Now, as I told you before, that there is one parameter which is known as the critical stress. This is the material property. The critical stress is equal to the Young modulus, the specific surface energy, and half A. A is what? Half of the length of the crack, internal crack, right? So there you saw in the previous slide, we have the total, like there is X, this is X dash. So this total was how much? 2A, right? But here we have only 1A. So 1A means it is half of the crack length. So the critical stress, because here you see the Young modulus is involved. Young modulus is material property. Brass has different Young modulus. The steel has different Young modulus. It is material property, right? So now material is involved here. So every material will have its critical stress value, right? So the critical stress value, always we should look here that the maximum stress, the stress at the tip of the crack should not be greater than the critical stress. If it is the case, what will happen? The crack will propagate. And once the crack propagates, the fracture will occur. Right? So this is an important point. Whenever you are designing something, you should keep it in mind that the critical stress must always be less than the maximum stress at the tip of the crack. Understand? Any confusion here? Now this specific surface energy for ductile material, we have Ys plus Yp. Yp is what? This is the for ductile material, we have the plastic deformation also. So the plastic deformation energy is, I showed you, if you plot here, the ductile material plots, what we will have? We will have this type of curve. Now here, beyond this point, this is the total energy absorbed by the material within the plastic region, right? So this gamma P is the plastic deformation energy, while gamma S is the energy before it. So in the brittle material, we have only this energy, while for the ductile, we have both. So that's why for the ductile material, we put this gamma S is equal to gamma S plus gamma P. So this is another good point, that whenever you are designing, you should take care of the critical stress. And the critical stress will tell you when your crack will propagate or it will not propagate. And what is the condition? The condition is when the maximum stress. The maximum stress is what? I explained you here. This is the maximum stress. You see this one. The stress at the tip of the crack. So once this stress is more than the critical stress, then the crack will propagate. Otherwise, it will not propagate. And one important thing is when the cracks is larger, that cracks propagates faster. So the critical stress is the applied stress? No.